It's a genuine privilege to introduce a friend, a mentor, and a former supervisor as our next speaker. Dr. Joan Ferrini-Mundy is president of the University of Maine, president of the University of Maine at Machias, vice chancellor for research and innovation for the University of Maine system, and chair of the system's science advisory board. As she mentioned yesterday, she earned her PhD at the University of New Hampshire. 1 year later, she received her first NSF grant, increasing the mathematics participation of New Hampshire girls, thus beginning a career-long commitment to encouraging women in mathematics. At New Hampshire, Dr. Ferrini-Mundy was promoted to the rank of professor. Later, she was a distinguished professor and associate dean at Michigan State, with appointments in both mathematics and the College of Education. Her distinguished academic career includes more than 100 publications and 10 PhD students. Dr. Ferrini-Mundy's national service includes serving as the director of the Mathematical Science Education Board at the National Academy of Sciences, during which time she was chair of the writing team that produced the NCTM publication, Principles and Standards of School Mathematics. At the National Science Foundation, she was a program officer, the inaugural director of the Division of Research on Learning in formal and informal settings, the assistant director of the Directorate for Education and Human Resources, and the foundation's chief academic officer. Among many honors, Dr. Ferrini-Mundy is an elected fellow of the American Math Society and the American Association for the Advancement of Science. She received the Louise Hay Award from the Association for Women in Mathematics for her contributions to mathematics education. And as a member of the federal government's Senior Executive Service, she received the Presidential Distinguished Rank Award. Please join me in welcoming Dr. Joan Ferrini-Mundy.
Good afternoon, everybody. Thank you so much, Jim, for that very generous and long introduction. I'm delighted to be here. This is a conference that I've known about for a long time and have heard about from my friend Jim Lewis. And it's just a pleasure to be with you all today. Thank you to the organizers. Thank you to all of the students and participants who are with us through this meeting. It's just fabulous. So thank you for having me. I was thinking for a bit about a subtitle to this talk after I submitted it, and I don't really have a great resolution. I was thinking I could call it Problems in My Life, or Problems that have made a difference for me, or something about problems, because it is a mathematics conference and I figured it better include problems. So maybe I'll just say it's about 10 problems. And I'm going to tell you a bit about the story that goes with each of these 10 problems. So we'll go to the next slide, please, Alex, thank you. So the first problem that I wanted to share with you and tell you a little bit about as a kind of key problem in my life is here. And some of you, but maybe not too many of you, will remember when high school algebra textbooks had problems like this as a standard kind of problem. And they would be in long lists of the word problems that would go at the end of sort of whatever the section was on manipulation of various kinds of algebraic expressions and solution of equations. Then there would be these sort of applications. Now, whether anyone ever really needed to know the answer to a problem like this didn't matter. This was just the sort of problem that appeared. And I have this extraordinarily vivid memory of being in high school and being assigned problems like this and having a very clear, easy way to solve them, but wondering, first of all, how could we really understand a problem like this better? You know, it's sort of an artificial setting. And in my head, at least, designing a little sort of a device that would be a bathtub where you'd be switching faucets off and on and showing the rates of filling the tub and allowing the students to manipulate that and tie that somehow to understanding the problem. Now, that was a fairly naive kind of notion for mathematics education in my early days. First of all, why would you build a whole manipulative around bathtubs? It wouldn't be very applicable in other kinds of settings, but it was an early indication to me that what I cared about a lot was whether people actually could understand the mathematics that they were being asked to do and give it any kind of context. And so I keep this problem in my files simply because it really was the first time I remember thinking about I'll bet we could do a better job helping people learn and understand mathematics. I had no clue what that looked like, but I've had a lot of occasions to learn a whole lot more about what that looks like. So with that, I think then the next slide, please. So a second kind of problem in my life has to do with license plates. And a little bit of a story on this. My husband is also interested in mathematics, but never studied much mathematics formally. His field is business. But when we first met and used to talk and go for rides and so forth, I learned that he had this habit of looking at license plates like constantly, and either casting out nines, which is an old thing where you add up the digits and look to see if the result is a multiple of 9, or factoring, making prime factorizations out of these numbers. And I just thought it was sort of interesting when I randomly tried to find a license plate that I could use for this particular talk, that 9151 is prime. I thought my husband would probably love that. I haven't shown this to him yet. But this thing about kind of always watching for math in the world around you was something that we shared. And I'll tell you a bit more about how that's affected us over time. Next slide, please. So in 1984, the very first International Mathematics Education Conference that I attended was in Sydney. I'm sorry, it was in Sydney, Australia. It was the International Congress of Mathematics Education. I gave my first talk at that meeting. I was terrified. And of course, it was a big trip and lots of time to be worried about giving the talk and being involved in this conference. But they offered side trips, tours that you could take to nearby areas. And we were fortunate enough to go and visit Tahiti as a part of this very elaborate trip. And in Tahiti, we were on a little tour. And in the car with me, and these are not names that probably too many of you would know, but Jim Lewis will know them, I know that. Sam Greitzer, who was a mathematician famous for his work in competitions and working with students in the International Mathematical Olympiad and elsewhere, and Shirley McBay, who was a math educator, very interested in issues of equity. And anyway, Sam Greitzer, Shirley McBay, my husband and I were in this car doing this tour of Tahiti, and a car ahead of us stopped, and my husband and Sam Greitzer together like instantly factored the license plate, which I thought was just kind of a weird little connection that only math people would even think was interesting, and maybe it isn't. But anyhow, it's just been sort of pervasive. So my memories of that first conference are very rich and interesting, in part because of an extensive way in which mathematics has pervaded my life. Next slide, please. Okay, so now we fast forward to a couple of years ago. This is my son, Joe, and his wife, Sarah Jones. And so Joe Mundy and Sarah Jones were married. And during the ceremony, they both made a few remarks about what it was going to be like to become a part of each other's family and so forth. And Joe said something sort of predictable. Sarah, in front of this whole audience, said, well, she said, you know, Joe had been to my house a few times, and around the dinner table, we would tell jokes and talk about our day and so forth. She said, I get to Joe's family for the first dinner. And one of the first things they asked me is, what's your favorite number? And she said, you know, I just knew that it was going to take some time for these two families to figure out how we could be close with each other. And I thought, you know, that's really probably very odd. But in fact, it was the kind of thing we talked about. The kids talked about mathematics and made it a part of their lives. And I'll come back to more examples of that later. So I wanted to share the license plate problem simply to suggest that something that you love and that you care about and that you like to talk about and think about, there are ways to bring that to a level where it's quite shareable with people around you. And in my experience, at least, that's meant a lot. It's been a rich part of my own life. Next slide, please. Okay, so problem number 3 of the problems in my life. This game, Sprouts, invented by the mathematicians John Conway and Michael Patterson at Cambridge, may be a game you know. It's a paper and pencil game, and it requires 2 players. And basically it begins with a set of dots on a piece of paper, and player 1 starts by connecting 2 of the dots and placing a 3rd dot in somewhere on the arc or segment connecting the first 2. And then the next player also joins 2 dots, but now there are some rules. No dot can have more than 3 three segments coming from it. And so certain dots get used up. The lines can't cross one another. And so you see how the game proceeds. Then the third player makes a move and they add another dot and so forth. And the game ends when a person it makes the last move, essentially. When there's no more move to be made, the previous person wins. So when I was a junior in college in a mathematics education course, actually, the professor gave this assignment. He simply explained the rules of sprouts and said, analyze sprouts now and go off and don't come back until you have something for us. And that was amazing to me, because remember, I was the person with the fill the bathtub problems. That had been my experience. A lot of sort of formulaic, relatively uninteresting problems that I did feel probably someone thought were important to learn. So I was interested in how people could understand them. But this idea of exploring something, and he would give no further guidance, right? It took us into, well, maybe we could try starting with 3 dots. What does that look like? What if, what are the strategies? What are the ways to win? What are ways to be sure you will lose? So on and so forth. But I just have a vivid memory of how things opened up. I was not doing mathematical research as an undergraduate, as so many of you, of course, are, but I had that same feeling of what's it like when you try to explore an idea and see how far it can take you. And so it's kind of still for me a meaningful problem, and I share it with you here. Next slide, please. Another meaningful problem around the same time that led quite directly into my professional work in mathematics education early on was this, generally, the challenge of finding volumes of solids of revolution in calculus. So I taught calculus for years. As a graduate student, as I looked at the subject, I began to think about, I kind of was back to the bathtub thing a little bit. Would there be ways to help students with the visualization? And remember, this is sort of pre-computing power available to the teaching activity. If you were going to show students a way to imagine and visualize this, you actually needed some kind of props or some sort of way to make really careful diagrams that were difficult to draw, but yet, of course, a fundamental topic in first semester calculus. So when I began to teach calculus or tutor students in calculus as a graduate student, I became kind of interested in how do students really make sense of these techniques? Do they need to? And if they can, what will support that sense making? What are the best ways to show these kinds of representations in ways that students can visualize them and then connect them to the mathematical work that's involved? So this problem stuck with me for a pretty long time. We can go to the next slide. I was working on my dissertation in the late 70s. And of course, doing that in mathematics education involves understanding the literature in the field where you wish to work. And that's iterative. As you begin to formulate your own research problem, that takes you to very specific literature. But I was very interested in data at the time about differences in performance and success in mathematics between men and women. I was very concerned with gender differences. We were seeing smaller numbers of women in mathematics. Fortunately, that has largely changed over the last couple of several decades. But in those days, it was important to understand, in my view, what is it about this? Why is it that we simply are not seeing the numbers that we need to see? And so the literature was very rich in those days in the 70s with survey articles and connections to the psychological literature, speculation about what might be the problem for lack of participation of women. And this is just one of the many, many papers that I'm sure that I did read when I was preparing the dissertation work. And it was about spatial ability, which has to do with ability to visualize and to turn shapes in your head and to be able to predict the results of moving shapes in certain directions and so forth. Something that I hope you'd all agree is pretty fundamental to much of mathematical thinking and mathematical reasoning. And it turned out that in the area of spatial visualization, spatial reasoning, performance on standardized kinds of tests for this were demonstrating differences by gender. Women performing less successfully than men in many, many studies. And so this report, which was written by the very, very prominent mathematics educator, Elizabeth Fenema, she was at the University of Wisconsin, caught my attention, and I sort of combined it with this curiosity I had about the solids of revolution, and essentially did do a dissertation study that looked at whether you could kind of train spatial ability to get better. And the basic result was that that women could improve, and that it was related to their performance in mathematics, particularly in calculus, particularly around the rotation of solids problems. A little story about Elizabeth Fenema. She was quite a legend in the area in which I worked. And in my field, the major professional association, one of them in education, is the American Educational Research Association. And so I dutifully submitted a proposal to speak about my dissertation when it was done. And I waited for the program to come out and to be accepted to give my 15-minute talk, and I was, and that was all good. In math ed, there's in education generally, actually, often a tradition at professional meetings to have discussants or critics after talks are given. So the talk is given, or maybe a set of talks would be given, and then someone critiques the talks. And those can be, in my days of going to those meetings, those could be fairly challenging. The critics could often be rather sharp in their commentary, and always helpful, but it became kind of a little bit scary sometimes. So I open up the program for AERA. I'm all excited about what's going to happen. And Elizabeth Fenema is the critic for my talk, which absolutely completely terrified me, because I thought, oh my gosh, this is like right in her area, and how's this going to go, and how's this going to be? As it turned out, she was unable to come, and a graduate student of hers gave the critique, and she was critical but really helpful, so it was all okay. But the point is, the connections that you can make across areas that are of interest to you are things that you should pursue. We heard talks today where folks working in persistent homology needed to learn some coding to be able to solve the problem they wanted to solve. And so much of that is happening today in mathematics, looking for ways that ideas connect, and then finding the key leaders who can be helpful to you, really an important part of progressing in these fields. We can go to the next one. Okay, so the fifth problem that I wanted to share is really just one of my favorite theorems, and it's very elementary, and I know this, but I always found it amazing that you could make a circle out of any 3 points. And I'm sure I talked to my children about this because I found it so amazing, and I'm not certain that they found it all that amazing, because, it takes a certain kind of point of view. But I have to say how delighted I was when my son, the one whose wedding picture you saw earlier, as a freshman in high school in a geometry course, needed to choose a project. And he needed to take something fairly significant and kind of work his way through the proof of whatever the thing was. Well, this was not elaborate enough, but if we can go to the next slide, what he chose, or well, sort of what I helped him choose, was the 9-point circle, which is tied to my favorite theorem, because it has to do with circles and how they come about and so forth. So again, as I was preparing to be a teacher of mathematics, of course, geometry was an important subject for pre-service teachers, and it still is today. It's taught in the schools. And so I had studied this in college, but when Joe was assigned this, I said, oh, Joe, we will have the most fun doing the proof of the 9-point circle and verifying that indeed, given any triangle, a 9-point circle can be constructed from it, and you can figure out what the 9 points are, and you can show that that will make a circle, and so on and so forth. And I don't recall any tremendous enthusiasm from him on this, but certainly it's another place where I found a connection. I texted him recently to remind him about this. I didn't get a whole lot back, so it's more in my memory than his, but nonetheless, this notion of being able to share the wonder of mathematics and help other people, frankly, help them understand something complicated. That's rewarding too for everybody. So that's kind of another piece of my story of problems. Next one, please. Okay, so this is number 6, and this has an asterisk because I could not locate my algebraic topology textbook. that I learned from in graduate school. And so I found a problem here in this collection, and I can't be sure in any kind of way that this is close to the problem that precipitated the story I'm about to say. But here's the story. So the PhD program that I was in at the University of New Hampshire was essentially a mathematics-based program in math education. Everybody took the same comprehensive exams in mathematics. Everybody had the same course requirements. That has shifted over time there and in other places. But these math ed degrees that were formed in the 70s, late 60s and early 70s in math departments. So Michigan State is another example. They had one at Michigan State. They grew out of, the math ed degrees grew out of mathematics degrees, with the leaders often being people who'd been involved in the new math. So going back to the 50s and 60s, mathematicians who had worked to try to improve K through 12 mathematics, got interested in these questions of teaching and learning, wanted to have students in their own fields be interested in mathematics education as well. And so anyhow, long story, but that's how I came to be taking algebraic topology as a part of a mathematics education degree, which was great. But I remember early on, I was in this course with my friends. Professor was terrific and fine and understanding, but we found the subject sort of significantly more complex than what we'd been studying up until then. It was hard. And I can't even tell you, if this problem was the one, as I say, that we were thinking about, but I remember distinctly my friend Tim saying, no, I'm clueless. There's no way that we can do these problems, right? He said, so next slide, please. So can somebody find a compass? Because he said, I think we need some diagrams and there will be circles in them. And if I could find a compass, I could make a beautiful looking solution that would probably be wrong, but at least I would be careful with the diagrams and with the illustrations. And all of us kind of breathed a sigh of relief and realized that we would be able to make our way through it by working together, very close cohort of graduate students that I was a part of. And we did work together, and we teased Tim for years about trying to get through algebraic topology by showing off by drawing his diagrams with a compass. Tim Kelly went on to be a very distinguished professor at Hamilton College after he finished his PhD and did just fine. So this is probably not a big part of the past for him. Nonetheless, these are hard subjects, and I think the value and the challenge of being able to understand and to make progress is well worth that challenge. So we can go to the next slide, please. Okay, another important problem for me for lots of reasons. In mathematics education, this field spans a wide range of types of work. There are people whose work is fundamentally research. It's about discovering new knowledge, understanding how people learn mathematics, understanding how to support them. There is curricular work, which is about creating the materials from which we learn mathematics in ways that are meant to support student learning. Research and curriculum development are often quite intertwined. Sometimes the same people who do curriculum work are doing research work. Teacher preparation is another major area of work in mathematics education, knowing that the best preparation of teachers is essential really to helping a next generation be able to understand mathematics. So there are those who study teacher knowledge and the ways in which teachers come to understand mathematics and how they work with their students and many other fields. In any case, this problem about patterns of swimming pools with borders became sort of a classic in various parts of the math ed world, used in curriculum work, used to study student questions about learning and related areas. And so the basic question is, you have swimming pools, those are represented with blue, that's I guess the water, and you have borders around them, tiles. And sometimes the question would be posed this generally, explore the patterns. Other times there could be more specific questions framed around this, but the problem and variants of it began to show up in a lot of places. And I was involved and had colleagues who were working in curriculum development. And I was getting more interested in how young children learn mathematics because my own kids were young. So if we can go to the next slide. I brought together sort of my professional life and my family in an article that I prepared with my colleagues at Michigan State, Glenda Lappin and Betty Phillips, with the swimming pool problem, where I posed the problem to my daughter who you see here in an article that we published in Teaching Children Mathematics, where we did some description of the way in which students attack this kind of problem, what they get interested in and what they do. And I only provided a small excerpt here, but for those who work in mathematics education, very often a part of the work involves reading student solutions or interviewing students or watching students in a classroom and working hard to make sense of what they are thinking. And to do that actually requires a fair bit of mathematical skill as well, because one needs to take the student very seriously and try to superimpose some sort of structure or frame on what they're saying. This article was meant for teachers, but I did want to point out that my daughter made a first sort of appearance in the mathematics education world in this article. We'll go to the next slide. Same daughter, fast forward now to many years later, is a 4th grade and 5th grade math teacher. And she shares frequently with me what her students have to say and what they're doing and what they're thinking and how she helps to motivate them. And she was telling us over the holidays that she goes to get her coffee every morning and brings the slip into her 4th grade classroom. And guess what the students do with the number on the slip? Remember the family thing. They figure out if they can factor the number, if it's prime, whatever they can do with it. And so we can go to the next one. She looks for ways to keep them motivated and keep them interested. And some of you may remember that a few years ago, there was a soup that Campbell's Chicken Noodle Soup was advertising that there were 32 feet of noodles in every can of soup. And my daughter was able to use that with her 4th graders to say, do you think that's true? And then they were able to say, well, maybe we could actually measure the amount of noodles in a can of soup, which went on to my daughter buying a can of soup and the children extracting the noodles from the can of soup and laying them out on paper towels around the classroom and measuring and so on. But I take a tiny bit of credit only because we tried to create an environment at home where talking about math was natural. Take a tiny bit of credit for a daughter that I believe is doing a pretty good job with her math teaching by keeping these kids engaged and finding ways to motivate them and to animate their learning in ways that help them make sense of things. So we can go to the next slide. Okay. 9th problem. I have to slow down a bit and give more context for this. Those of you who follow mathematics education will know that in the last couple of decades, maybe 3 decades, there's been a fairly significant set of shifts and new ways of thinking about teaching and learning, particularly in the elementary grades for children. And a large discussion, if you watch this history, has gone on for years about what are called standard algorithms for arithmetic operations in the elementary school years. So probably if all of you on this call were asked to write down how you probably were taught to solve this problem, we would see some variety based on your age. Because over the years, there has been a trend in some curricular areas to move a bit away from what one might call the kind of standard ways of recording the subtraction algorithm, and rather to move to other representations that are intended to be more meaningful or to help students understand the operation of subtraction and so on. So this problem, keeping it in mind, I think if you click, we should get an animation here. All right, so having said all that about the standard algorithm, here is a solution representation for this problem, and I'll let you look at it for a second. You see, I'm sure that it's adding up from the 35 to get to familiar or convenient numbers so that then the student can eventually get to the answer and keep track of what got added on, keeping track as they go, and then concluding that the answer is 46. So the problem here that we're talking about came to me from a colleague when I was at the National Science Foundation, and the colleague came to us and said, okay, my granddaughter is trying to do this problem, this 81 minus 35, but here's how they're teaching her how to do it in school. And I know how to get the right answer, but I can't figure out what she's doing. We can go to the next slide. So my colleague Karen King, the late Karen King, a wonderful friend and tremendous math educator, and I and others put together something that we called Help Your Kids with Their Math Homework over lunch when we both were working at the National Science Foundation. The idea was to see if we could bring together staff from all over the agency, if they were interested, to get to talk about math. Right. So my family dinner table thing, I just kind of wanted to extend that to my colleagues too, and see if there was a way we could perhaps find some interesting new connections and be helpful to people. And by saying, how would you like to help your children with math, we were able to also entertain questions that people might have for themselves. So we posted this sort of offering to have a lunch hour sessions and encourage people to bring their kids' homework. And so here you see Karen working with one of our colleagues. Part of the approach to this actually was for us to try to model what we would like the parents to maybe do with their children. So we very rarely explained anything. We would have the colleague go up to the flip chart here and write the problem down, and sort of we'd ask questions, and then others would begin to ask questions. They're quite fun. I can't remember, Jim, if you ever were able to come to any of those sessions, but the ones we had were good. And so I'll tell you just one anecdote, and then I'll come back to the subtraction problem. We had a fellow who came because he had two daughters that he thought were really kind of pretty good at math, and he was pretty sure he hadn't been good at it. And they were, let's say, in Algebra 1 and Algebra 2, roughly. And he turned out to actually be very, very strong. Once we got him up there at that flip chart, trying to work his way through the problems that his kids were having trouble with, he had these great aha moments where he would say, oh, I can figure that out. And so I remember the first time he came, he said to Karen and to me, I've got my kids, I'm taking them this weekend to a Nats game. We're going to a baseball game, and I'm going to do algebra with them at the baseball game. And I said, well, that might be over the top, but see how it goes. Give it a try, see if it works. And he was loyal. He came to a lot of our sessions. But the previous problem, the one with the subtraction, was a staff person of longer standing at the agency. She wanted to help her granddaughter. She was pretty sure she knew how to get this problem right, and she was really embarrassed to be bringing an elementary school problem. She said, I don't know if I should come. It's kind of, I feel sort of silly. And you can't believe how people just gravitated around, and we got her at the flip chart, and she figured it out, and all was fine. But it can be a unifying factor, mathematics. It really can be a way to bring discussion into organizations and groups that you maybe aren't sure are interested in that discussion. And that, for me, as a person in education, has always been very rewarding, because if we can help people like our subject, see it as useful, understand how to make sense of it, I just think that makes the world a better place. And if we can help make that possible for all people who are interested in mathematics and want their kids to do well. So next slide, please. Okay, and so we're shifting a little bit now. These kind of follow the trajectory of my own experience. And I did spend several years at the National Science Foundation. And so my 10th problem in my batch here is about the National Science Foundation. And every year, the National Science Foundation needs to make a budget request to the Congress through the president for their funding for the next year, because, as you know, this is a grant-making agency that is in place to support and advance the progress of science across the nation. And so to do that, dollars come through the Treasury, through taxpayer-funded programs that we then at the NSF that are then the programs that push money back out to the very best in the field. And I've been hearing a lot about REUs and people who've had a chance to work on NSF grants here. And that's just fantastic, the way that our system works, because the government pays for the engagement of folks in research. And it pays for that across, the NSF pays for that across multiple fields. So the NSF has several directorates and they're familiar to you, of course, the Directorate of Mathematical Sciences, computer information science and engineering, geosciences, and so on. And there is an education directorate as well. And I worked there with Jim Lewis, actually, together in the education directorate. And by the time I hung around long enough, I became the head of the education directorate, and I paid a lot of attention to the budget. So this came before me one year early on in my time, actually, and it made me really curious, because if you look at this slide, you see information about research and development, basic research, applied research. You see the dollars going to that. You see the request for the next year. And reading down through R&D facilities, so think telescopes and ships, research vessels, and major kinds of physics equipment and so forth. And then you read down to education and training. And education and training is pretty much where the education directorate's dollars were categorized. And I started to get interested in these tables because, to me, to move education in mathematics or science or engineering or technology, to move STEM education forward, my view of the world was that would take research, that we needed to understand these questions of teaching and learning much more thoroughly in order to make efficient and impactful investments through the programs of education and training that are listed here. So I got really interested in, how do we get dollars going into EHR, the education directorate, that will support research in the same way that the mathematical sciences research is supported. Not at the same scale, but certainly with the same notion that there's new knowledge to be had through educational research, through disciplined, systematic work. And so this is a problem that represents, I think, something of a shift in the types of problems I'm sharing. But let me go on with what we did with this. To the next slide, please. So every year, as I mentioned, NSF makes the budget request to the federal government, and then frequently there would be follow-up hearings and queries from the Congress about what did you really mean by this. And we were on a path in education to try to build more research in. So I'm going to now try to make a fairly tenuous argument, which is frightening in front of all you mathematical people, because it probably has a couple of holes in it, but I'll give it a shot. We would be expected to write text that would go into the printed budget that would make our argument for why we needed to do whatever the thing was that we were asking for money to do. And so here is an argument we made, and I want to sort of claim, and see, take it for what you will, that my mathematical training and years of trying to think about what mathematics is and justification and how to help people understand it, there's a little bit of that involved in some of this, right? We start here with an assumption about what EHR, the Education Directorate, does. Then we essentially make a definition, really, of what core is, right? Every part of NSF has had a core R&D investment line, and we, for education, decided we were going to request that same kind of line in our budget for a core research focus in undergraduate learning, or in K-12, or in broadening participation, and the various areas that we focus. So we were basically introducing a new idea here, trying to make an argument for it, trying to say it would have an impact. There would be a result at the end. We didn't fill in all the steps of the proof, because in fact that would have to happen through demonstration. But we really found ourselves in the business of needing to try to make a case. And I would like to think that years and years of doing mathematics maybe helped with making cases. We did have some success with this, but it's a constant challenge to be sure that education keeps a partial focus on building our research knowledge so that we can improve learning as we go. So next slide, please. And I didn't put a number on this one because it was just harder to frame it in any way that remotely resembled a mathematical problem, but I am a university president, and we are in a pandemic and have been for some time. And so when headlines like this one on the left began to show up in March of 2020, and I began to talk with all of our colleagues across the country and within our system and university here, began to think about our students, our population, our faculty, and our staff, and what this would mean for us. That was pretty uncharted, new territory, very new problems to think about for pretty much all of us in this business. And so that's been going on, as you all well know, given your own circumstances, been going on now, coming up to 2 years of this, with an awful lot of mathematics woven through the discussions and the decision-making and the translation of ideas to everyone. And so again, I can't really directly claim that algebraic topology helped me prepare for this, but I can claim that being able to try to make sound arguments, being able to have conversations with really trusted colleagues and try to reach best solutions, those are norms of mathematics. And I like to make the case that it matters in the work that I do today. We're doing well, as so many universities are, but we right now are watching everything very closely because we are back in person fully at a time when the Omicron variant is surging. I have heard a few things, and I would be interested, in what people are saying. Certainly there are scientists and public policy folks and epidemiologists giving courses around pandemic issues in our universities across the country. I haven't heard a whole lot from mathematics and statistics, but my hunch is that those exist as well. There's so much mathematics right there on the front page every day now around this, and the need to the fact that terms like inflection point and flattening the curve and maximum and rate of change and so forth, that those are in our everyday lexicon, I think is actually pretty wonderful and amazing. I also find myself in great conversations with our statisticians and some of our other faculty about the difference between prevalence rate and positivity rate and what you can generalize and what you can't, and whether your testing is random or not. So there's a richness to this in the face of a very, very daunting international challenge, and mathematics again has a place to play there. So with that, I would close. Thank you for being with me and for listening to me. The motto of Maine, as you saw on the license plate, is vacation land. Right now, it's like 10 degrees or something, so probably not the best place to vacation unless you really like the outdoors when it's cold, but it's gorgeous in the spring, summer, and fall. And I do invite you to learn more about us and the University of Maine. And thank you so much for your time and your interest in this session. Thanks again.